Hello, my name is Monica Hansen, and today I'll be discussing chromaticity shift behavior in LED packages. This is part of an ongoing study I've been working on with my collaborator, Lynn Davis at RTI International. We have been working on looking at the long-term LED package lumen and chromaticity behavior for about 6 years, since 2014. And this work has been funded by the US Department of Energy's Solid State Lighting Program. Here's a quick disclaimer that the opinions expressed here are that of the authors, not necessarily those of the US government. So LED packages are a diverse set of platforms available today in the marketplace, designed to tackle an array of different lighting applications. The various packages and form factors can be grouped into four major platforms. On the left, there's the high power LEDs, which typically consist of an LED chip mounted onto a ceramic substrate with a molded hemispherical lens. These tend to be larger chips, 1 millimeter or greater in size. And these are used in applications that require high power and high reliability, such as streetlights and sometimes directional lighting. Mid-power LEDs is the second platform, and these tend to contain one or two small die mounted onto a metal lead frame with a resin housing molded around it and filled with a polymer containing encapsulant with phosphor particles inside. And it is a low-cost, high-volume platform in many lighting applications today, and mostly in omnidirectional applications such as troffers, flat panels, and LED lamps and bulbs. The third category is chip scale packages, which consist of a flip chip LED coated with phosphor to create a white chip. You see the phosphor around all 5 sidewalls of the LED, and the bottom is clear for the attach process. Some of the newer chip scale packages contain white sidewalls to block the side emission of the light and just to create a top side Lambertian emitter. These tend to have a small footprint for close packing to create an array with a very small source size. You can also tile together very tightly different color temperature LEDs if you want to have white tunable with a warm white and cool white CCTs. And then finally, we have chip on board LEDs, or COBs, which in this platform you consist of many small LEDs mounted to a metal core PCB or a ceramic substrate. And then these are covered with a phosphor containing encapsulant. And this platform is typically used when high luminance is required. With these 4 package platforms, there's a wider set of materials and methods of construction. And in this effort, we wanted to see how this impacts the LED reliability performance over time. So as part of the long-term study, we have reached out to LED manufacturers requesting LM80 data reports for analysis. And this work began in about 2014 timeframe, and we published multiple presentations and a report in 2015 about our findings in the behavior of different LEDs in terms of lumen maintenance and chromaticity maintenance. And so many tier 1 manufacturers have provided LM80 reports to this effort. We've collected over 400 records for a team to evaluate the LED level factors that impact performance and to provide insights into the commonalities observed across many manufacturers with respect to the LED package reliability in these various platforms. So as I mentioned, the first study embarked in 2014-2015, and we looked at data from LM80 reports all the way from 2011 to 2015. And then last year, we began a subsequent study in 2019 to see over the past 5 years how LED packages have improved since our first study. And so we will focus today on the LM80 data reports collected between 2018 and 2020 that are evaluated. And these newer reports are important for the study of chromaticity maintenance because they're aided by the much greater availability of LM8015 reports with individual U' and B' coordinates that are important for the analysis. So this presentation will focus on the newest data set. So just briefly about LM80, what it is. In 2008, a method for measuring the lumen maintenance of LEDs, LM8008, was established by the IES to provide a consistent way to compare LED long-term behavior. And this was combined with a projection methodology, TM21, to project the lumen maintenance behavior from the LM80 data using an exponential decay model as seen here. The decay rate constant alpha is inversely related to luminous flux maintenance lifetime. And so the value of alpha is then used to generate the luminum flux maintenance life projection from the TM21 standard. And just a quick note that this projection cannot exceed 6 times the test duration in LM80. And this is known as the 6X rule. So for example, if you have an LM80 report that tests the LEDs to 10,000 hours, the highest lifetime you can report is 60,000 hours. And more importantly for this study, in 2015, ANSI combined with the IES issued an update to the LM80 method for measuring luminous flux and chromaticity maintenance by requiring the reporting of the individual chromaticity coordinates U prime and V prime, instead of just reporting the chromaticity maintenance with the parameter delta U prime V prime. And this new standard LM8015 is what we'll focus on in the data sets today. So while this methodology for projecting lumen maintenance in TM21 was available in 2011, projecting chromaticity shift provide a much tougher task. The ability to project chromaticity shift for LED packages would help give the industry more information about the expected long-term behavior of LED packages that are integrated into luminaires. So after much work at the committee level for many years, ANSI and IES released a new projection methodology, TM3519, at the end of last year to aid in projecting chromaticity maintenance in the same way that TM21 is used to project lumen maintenance. So this projection is based on the differential chromaticity analysis method, or the DCA model, which allows a projection of future values of the U prime and V prime coordinates from the LM8015 datasets. The DCA method applies a curve fit to the data, looking at the differential chromaticities, and extrapolates the changes in relative chromaticity. And the outcome is it projects the time at which the magnitude of the chromaticity shift exceeds an acceptable level. For instance, when delta U prime V prime is 0.004, it's called CS4 in the report, and you can see that at the bottom of the table of the reported values. And then 0.007 would be corresponding to CS7. This TM35 report also includes a vector plot with the projected CS4 and CS7 hours shown graphically, but also the direction of the chromaticity shift. So previous studies that we've embarked on have identified 5 common chromaticity shift modes, or CSMs, that were seen in many LED packages and lamps we evaluated. And these are typically due to either thermal or chemical degradation of the materials within the package. For example, at higher temperatures or longer lifetimes, the materials in the LED package will start to degrade, discolor, crack, or even delaminate, which will impact both the lumen maintenance and the chromaticity shift behavior. Temperature effects, such as rising temperature in the phosphor particles, can also affect the rate of change in the color shift. And other materials, such as silicones, resins, and even phosphors, can undergo chemical changes that lead to the color shifts. So these earlier studies led us to classify most of the packages observed into these main categories in the table below. And you can see color shift mode 1 is a blue shift. Sometimes this occurs with annealing processes in the LED package during operation in the early stages of its life, but it can also occur in any packages when cracking of the encapsulant occurs, more blue light leakage happens. Color shift mode 2 in the green direction tends to occur in some warm white LED packages due to the change in the phosphors and more specifically, oxidation occurs of the red phosphor, which decreases its peak intensity relative to that of the green phosphor, leading towards a green shift. CSM3 is a yellow shift, and this has been a known dominant chromaticity shift mechanism for many ceramic-based packages and is often caused by delamination of the yellow phosphor layer from the dye. The CSM4 is a more complex mechanism that is observed in a lot of packages. It starts with a very initial blue shift, a short-term blue shift, which is then followed by a shift in the yellow direction. And then after a certain amount of time, the chromaticity point shifts backwards again and circles back towards the blue. And in this case, the final blue color shift tends to be the terminal color shift mechanism. And we see this in mid-power packages where the polymer photo-oxidize and absorbs some of the longer path length photons. And then finally, CSM5 is a shift in the red direction. This doesn't occur too often, but it does tend to occur in the warm white LED devices if there's changes in the green phosphor efficiency. If it decreases faster than the red phosphor deficiency, you can see a slight increase in the contribution of the red phosphor and thus redshifting the behavior. So moving back towards projecting chromaticity shift with TM3519. So we had these physical mechanisms that we had identified previously, and that's going to aid us in the analysis of the TM35 projections. So the DCA model, the way it's constructed, is it assumes there's 3 phases of behaviors from LEDs seen in delta U prime V prime over time. There is the first phase is the incubation, which is signified by a rapid short-term increase in delta U prime B prime, followed by an extended period where it is essentially constant. Then the second phase is a recovery phase. Sometimes the incubation period is followed by this decrease in delta U prime B prime for a portion of time. And then the third and final phase is emergence. And this is often considered the terminal chromaticity shift mechanism has occurred during emergence. And we see the approximately linear function of time increase of delta U prime B prime till you reach these thresholds such as CS4 or CS7 where you hit the 0.004 or 0.007 point in the plot. And it's going past its useful lifetime in terms of chromaticity shift. But please know on the lower graph, there's not always a recovery period observed in all packages. Sometimes you move straight from incubation into emergence, and often we see the recovery phase skipped at the higher stress levels. So the goal of this effort was to understand how accurately this new projection methodology, TM35, was at predicting the chromaticity shift of LED packages. We used 3 criteria to determine how well the projection worked. So the first criteria was the accuracy of the projections for chromaticity shift magnitude, or the total delta U prime V prime shift. At a minimum, you want these estimates to be conservative. For example, giving you a lower CS4 life or CS7 lifetime, since you do not want to project a longer chromaticity maintenance life and then have the package fail for chromaticity earlier than projected. The second criteria was the accuracy of the projections for chromaticity shift directions. It should predict a shift in line with the known physical degradation mechanisms for different package classifications. And then the third thing is you want to see a consistent pattern across the data sets for a given LED product at the test conditions that produce the same phase, for example, incubation, recovery, or emergence. However, the time at which these different phases do occur depends on the stress level. So keep in mind that these criteria are not mutually encompassing. For example, the model could accurately predict future values of chromaticity shift magnitude, but could do a poor job with predicting the direction of the chromaticity shift, or vice versa. So the data that led to this study, we analyzed 146 data sets that met the LM8015 reporting requirements. And 115 of those data sets had 10,000 hours or more of test data. To understand the ability of TM3519 to predict the future chromaticity, its accuracy relative to these three criteria was examined for all the LM80 data sets we acquired. The remainder of this talk will discuss representative TM35 case studies from each of the four major LED package platforms. So the first case study is of a high power LED under high stress operation. This LED was first tested at 700 milliamps and 120 C for 12,000 hours of actual operating life. And that's the blue curve, both in the left and the right plot. The data then was input into the TM35 DCA model, and the behavior was projected to 24,000 hours, or the red curve. So on the left, you see the chromaticity magnitude shift, and then on the right-hand side, you see the actual U prime, V prime coordinates, or the direction of the chromaticity shift. And what we see is this model provides a reasonable delta U prime, V prime projection, satisfying criteria 1. And criteria 2 and 3 also appear to be met from the projections, and they show a nice, clean continuation of existing data sets. All three criteria were met in this projection, showing that it was accurate for this particular product under normal test conditions. Now, looking at the second case study, we based this on the same high power LED product, but looking at a longer LM80 test duration time. So the first study, we looked at 12,000 hours. In this case study, we have the LED measured at 24,000 hours, but at a lower temperature. So it's 700 milliamps and 85 C instead of 120 C. And in this test condition, we only use the first 12,000 hours of the measured 24,000 hours of data, or the blue curve, to see how accurately the projected red curve met the real data. So you can see the extra data that we did not use in the projection up to 24,000 hours is shown in this gray curve. And it allows us to assess, if you only had 12,000 hours of data, how well does TM35 predict when you can actually see what happened up to 24,000 hours. And what we do see is that the projection is a conservative estimate for delta U prime V prime. It is showing a failure mechanism to the CS4 conditions at a sooner time than what the data is projecting. But we see differences in the chromaticity shift direction. So the projection on the right-hand graph shows a very strong shift to the green direction in the red curve. So the delta U prime, the change in delta U prime coordinate is very large. But then when we looked at the measured data, or the gray curve and the blue curve for the first 12,000 hours, and then the gray curve for the remaining 24,000 hours, we don't see quite such a strong shift. So it is indicating that maybe this is not satisfying criteria 2 in terms of accuracy of the direction. And so as we zoom in, we see that the actual data in the gray curve is, instead of shifting green, it is starting to shift up towards the yellow direction. So we're not seeing a consistent chromaticity shift direction between the different test conditions. So we don't meet criteria 2 and 3 in this case, just the conservative in nature. So moving to a third case study based on the same high power LED, we wanted to see the impact of the data measurement intervals in the LM80 report and how that impacts on how the model projects the chromaticity shift over time. So we compared LM80 data that is measured every 504 hours in this report to 1,008 hours. And TM35, the standard, does state that different results may be produced from the same data if the measurement interval is changed. So we wanted to see how sensitive this parameter is to the results. So in this case study, we did use the full 24,000 hours of measured data to feed it into the TM35 projection. And when we look at the 1,000-hour measurement interval on the right-hand side, the projection for delta U prime V prime is not conservative. It is estimating a CS4 timescale of 83,000 hours. But then when we use the 500-hour measurement interval on the left-hand graph, you see that CS4 is almost half the life that it was with the 1,000-hour increment. So this does not give a conservative estimate of CS4 lifetime when you're using the 1,000-hour increment, thus failing criteria 1. And also not shown here, but when we look at the projected color shift directions, it's not consistent, failing criteria 2 and 3. So after these 3 case studies, how does it stack up? So here on the table is a summary of the different measurement test duration hours, the interval, and the projected CS4 and CS7 lifetimes for these different conditions. So we see from the first 2 studies that the times to reach delta U prime V prime of CS4 and CS7 follow the expected trend, showing lower times at higher stress conditions. So you reach them faster, these color shift thresholds faster at 120 C than you do at 85, which is consistent. Then when you consider the difference in the test duration, it also strongly impacts the CS4 and CS7 thresholds. So when using an extended data set to 24,000 hours, you get a higher threshold value because the model was over projecting. And then finally, when we look at the comparison of the measurement intervals, this causes a little bit more concern. When we go to the 1,000-hour interval, then we see that the CS4 and CS7 lifetimes are not conservative. And this indicates there is a very high degree of sensitivity in the model to the measurement interval parameter. This is potentially an issue because the chromaticity projections that can be significantly impacted by what information an LED manufacturer provides in the LM8015 reports. A reported measurement interval could potentially be selected to improve TM35 projections beyond what it could be in real life. And it is important to note that most of the LM80 reports only provide up to 10,000 hours and 1,000 hour increments. This is very common, which makes it more of a challenge to accurately project the TM35 behavior. So moving on to a different package platform, case study 4 evaluates chip-on-board LEDs under different test conditions, different currents and temperatures. So for example, here we have tests at 85 C and 3,300 milliamps, and at 105 C and 2,400 milliamps. Here we are using the first 10,000 hours of data, and in the blue curve and the purple curve for the 2 different temperature and current conditions. In this study, the CS4 and CS7 lifetimes projected by the model in the red and orange curves respectively showed a much sooner occurrence at the lower temperature. So you're reaching these color shift thresholds much faster at lower temperature than you are at higher temperature, which is not consistent to what we typically see with the physical degradation mechanisms. So in this particular case, this data set fails our criterion 1 for the study. It's not a conservative estimate of color shift thresholds. The TM35 also projects significantly different chromaticity shift directions for the 2 conditions seen on the right-hand plot. At 105 C, you see a shift towards the red direction, whereas at 85 C, we see a shift to the magenta direction. And this is important because the predicted shift to magenta is a direction that we have not seen in physical data sets for white PC LEDs. So typically, you do not fail in the magenta. It would require a very challenging set of circumstances coming together simultaneously to result in the shift, which was never observed. For example, if the relative red emissions increase while the blue emissions are also decreasing simultaneously, then you could get a shift in the magenta direction from the data, but these 2 trends are mutually exclusive and unlikely to happen simultaneously in the white phosphor converted LED, because an increase in blue emission means that more photons are bypassing the phosphor layer and not being converted to increase the red emissions. So when we see a magenta shift, we know that there's something faulty in the prediction. And so the disparity in these two different shift directions for this data sets for the same LED package also violates criterion 3 with behavior that doesn't make sense. So shifting gears to the mid-power package platforms and how these behave in TM35 projections, we looked at a fifth case study where we used 10,000 hours of measured LM80 data, which is the blue curve. And we actually had the full 17,000 hours of data in the gray curve. We just used the first 10,000 hours for the projection. And then the red curve again is the projected time. And we see, as before in the high power platforms, that the projection for U prime V delta U prime V prime is conservative, that you're meeting the CS4 threshold before the full 17,000 hours of measured data would predict that you would. So it is passing criterion 1 as a conservative model. But again, as we saw earlier with the high power LED, there's a very strong color shift projection in the green direction on the right plot. You can see that delta U prime, the change in the U prime coordinate is overestimated, and it results in this strong green shift. But then when we look at the actual measured data, the 17,000 hours of data, it is not consistent with that, and it is corresponding with a blue shift. So this fails criterion 2 by predicting a green shift, which isn't accurate. So now taking that same LED product and putting the full 17,000 hours of the LM80 data into the projection, we look to see how the behavior will change. And we saw in the previous slide that the 10,000 hour data set was still in pre-emergence phase. It hadn't ended up in its terminal color shift direction. It was changing because it started going towards the green direction, but then it hooks down towards the blue after 13,000 hours. So when we're using the full 17,000 hours in the projection, the LED has reached its emergence phase or its terminal color shift. And in this case, we see that the model, though, is predicting it to be a terminal color shift in the magenta direction. And again, this is not a physical mechanism we've observed, so it's failing criteria 2. And typically the data is showing that we're going to have a blue shift, and the over projection of delta U prime, the change in the U prime direction, is resulting in the model predicting this magenta shift. So here again, we're failing the direction, and the challenges with having data to only 10,000 hours is we never reached that emergence phase, and it was not projecting accurately. But then once we finally got into emergence, at least the magnitude shift was a conservative estimate. And then finally, moving to our final and sixth case study, we looked at how the projections behave in a CSP LED tested under different stress conditions for 17,000 hours at 85C and 105C for 1,000 milliamp drive current. And we see the testing at different temperatures resulted in emergence being reached at 105C, but the LED was still in pre-emergence at 85C after 17,000 hours. This is a different phase status at the different test conditions resulted in a different predicted chromaticity shift behavior by the TM35 model. The pre-emergence, the CSP is showing a yellow shift, CSM3, and the post-emergence, the yellow shift actually turns back to the blue and is consistent with our CSM4 model where it goes blue, yellow to blue. So we see in this chart, and again, the projections are in red and orange and the data is in blue and purple, that we are seeing a conservative estimate for the projections, that we are reaching these color shift thresholds ahead of what the data predicts it to be. But we're failing criterion 2 for the color shift direction, because as the different stress conditions show, the 85C is projecting up to the yellow direction, and the 105C point is going down towards the magenta direction. So again, there's not consistency between these different stress points. So to wrap up, I'd like to discuss the lessons learned from these 6 case studies in how TM35 projects the chromaticity shift mechanism from the LM8015 datasets that we collected from a variety of Tier 1 LED manufacturers. The model is a conservative projection for the magnitude of delta U prime V prime in LED packages, or the predicted CSX time is actually less than the real time. So you want it to be conservative so we don't have a challenge with premature failure. In particular, the model works best when the emergence phase is known and there is at least some data to indicate that emergence has occurred. That is when we see the most accuracy. When we are pre-emergence, we see that the color shift projections and often the magnitude can be inaccurate. The model doesn't appear to accurately predict the direction of chromaticity shift for most of these packages. The chromaticity point predictions do not coincide with the known physical degradation mechanisms of the types of LED packages being evaluated. And sometimes you have predicted color shifts in non-physical mechanism directions. There's also a high degree of sensitivity of the projection accuracy with the length of the LM80 test measurement interval. And this is the biggest concern because often 1,000-hour intervals are used, but as we get to the 500-hour intervals, we see more accurate data projections. And also 10,000 hours is a typical report. And in certain cases, as we saw with some of these LED packages, the emergence phase has not been reached in that 10,000 hours. So really the length and projection interval of the LM8015 reports is of critical importance on the accuracy of the TM35 methodology. So, however, even though there's these shortcomings that had been identified with the TM35 model, this model could be beneficial to lighting industry provided that its limitations are recognized. And in many cases, the magnitude of color shift is a conservative estimate. So as long as we take it for what it can do well, there can be benefit. So I would just like to acknowledge Key Logic, the government contract administrator for the U.S. Department of Energy, for administrating this contract. We'd also give a big thanks to the companies that provided the data sets for this analysis over the course of many years. If you have any questions, here's our contact information for both myself and Lynn Davis. Feel free to reach out and we can follow up with any more information. And I'd just like to leave you with some links for other resources in data that we published and reports that are out there. So there's general information on chromaticity shift and also more detailed information on this analysis of the LM80 data and the projections with TM35. So thank you very much for your attention.